everybody, it's Miss B, and welcome back to another physics video. Now, for the past couple of weeks, we have been talking about how to calculate motion, such as speed and acceleration. We've also been talking about how you can look at speed and acceleration on a graph and calculate it, and how these two look very different. So these are concepts that you should feel comfortable with now, and if not, please feel free to do some more practice questions or send me a quick email so that we can talk some things out and make sure that you have a complete understanding. Now, instead of talking about how to calculate speed, acceleration, distance, or time, we're now going to be talking about why. Why is speed relevant, or acceleration, and how these things were actually discovered, and the theoretical bases behind each of them. Now, in order to do this, we are going to dive a little bit into history and learn a little bit about the men who started with the physics of motion. So you can thank these three gentlemen for today's lecture and for this entire unit. The first gentleman we're going to be starting with is Aristotle, who started his physics journey way back in the 300 BC era, quite a long time ago, over 2,000 years ago. Now, Aristotle, as you may know, was a Greek philosopher. He was actually a student of Plato, who was one of ancient Greece's great philosophers. Now, what really helped Aristotle was that he came from a very wealthy family. His father, an aristocrat, was the personal physician to the king of Macedonia. Now, unfortunately, his parents did die when he was 10, and he was raised by foster parents. However, he was still able to have a wonderful life and be able to make some amazing discoveries and some forward-thinking notions into what we call physics. Now, Aristotle was a fairly well-off gentleman, and because of that, he was able to become a philosopher. He had a lot of extra money, so instead of performing experiments like you think of as modern-day scientists, philosophers didn't really do that. Philosophers more sat and thought. He used logic and reasoning behind all of his ideas. He never really tested them out. He just observed nature very carefully and explained what he was observing. And that is what made him a philosopher. Now, although Aristotle is held with very high regard, he did make quite a few mistakes along the way. One really big mistake was that Aristotle killed the atomic theory for 2,000 years. Now, a random guy named Democritus proposed that everything was made of small pieces called atoms. But Aristotle said, no man, everything is made up of the four elements: earth, wind, fire, and water. Now, you may remember, hopefully from our chemistry unit, that indeed everything is made out of atoms. Now, because Aristotle didn't believe this theory that Democritus had proposed, and he had a very big following at the time, a lot of other people decided to side with Aristotle. And because of this, the idea of atoms disappeared until 1810, when Dalton reintroduced them to the world as his new atomic theory. So because of Aristotle not believing in this theory, he actually delayed this scientific discovery for an extra 2,000 years. Now, Aristotle was also the guy who is responsible for the theory that everything is made up of earth and air, as well as fire and water. Now, hopefully, if you remember our chemistry unit, we now know that everything is actually made up of our basic elements from the periodic table, not actually from these four elements. However, it is important to give Aristotle some credit where it is due in saying that he was the first one to start breaking these ideas down and actually questioning what things are made of or how things move. In fact, he was one of the very first people who is known to have tried to explain motion. And he had a few different ideas that he gave to people around him. One of the very first things that he talked about was that objects have a natural tendency to come to a state of rest. And if you want something to move, you have to push it. Basically saying that if something is moving, there is a force behind it that is pushing it. And that if you stop pushing that box or cart, it's going to stop moving. Now, this may seem fairly basic, however, he was the first one to actually notice this going on and talk about it. He also had another idea about objects tending to move towards the center of the universe, namely Earth. Now, he called this natural motion and said that it was always happening vertically, meaning up and down. So if something was moving up and down, like me dropping a pencil on the floor, that meant that it was natural motion. It was going to happen effortlessly. And this meant that some motion really confused Aristotle, such as things that moved from side to side, like Katniss releasing a bow and arrow. We always wondered why that bow and arrow continued to move if it wasn't going naturally up and down towards the Earth. Now, he believed that horizontal motions, like shooting an arrow, were unnatural because the arrow would not naturally move that way unless it was being pushed by something. So now he had to come up with an idea to explain this phenomenon. And to do that, he came up with this idea. He said that projectiles move because of air rushing in behind and pushing them forward. So I'll give you an example here. Say I threw a baseball. He had this idea that when the baseball moved forward, it actually created a vacuum behind it, meaning that there was nothing there, and that air would then swirl to fill that vacuum, and the air swirling behind the baseball would now push the baseball further forward. Now, there are quite a few inconsistencies with this theory. However, it was a stepping stone in the right direction. Now, Aristotle's explanations didn't satisfy everyone. But because he was held in such high regard by other thinkers, his opinions were not seriously challenged. Many didn't want to go up against him because he was held in such high regard by the rest of society. For more than 1,000 years, his view of motion formed the scientific understanding of moving objects. Now, Aristotle stayed pretty popular until another guy came along many, many years later called Galileo. I am not talking about the guy in that Bohemian Rhapsody song. I'm talking about this dude right here. And he was born in 1564 and died in 1642. May seem like quite a while back, now that we're in the year 2020, but he is a lot more hip and modern than what Aristotle was. Now, this guy actually did some pretty innovative things for science, and a lot of astronomy as well. He invented the telescope, and with it discovered sunspots, as well as 4 of the largest moons of Jupiter. Now, he didn't just keep his head in space, he also looked at the way things move around on Earth. One of the things that he studied was falling objects. He would conduct different experiments with different weighted objects to see if they would fall at the same rate towards the Earth. And he concluded that yes, regardless of weight, objects will fall towards the Earth at the same rate. You can watch some really cool YouTube videos seeing, a feather and a bowling ball being dropped at the same rate and seeing if they hit the ground at the same time. Take a look. Now, Galileo is kind of different from Aristotle. Where Aristotle sat and thought and observed all the time to make his ideas, Galileo was a lot more of a doer instead of a thinker. He actually is considered the father of modern science, and this is because he was the first person to do actual experiments to justify his ideas. He wanted to make sure that his theories actually worked out, and he tested them using scientific experiments. So you can thank him for all of those experiments that you usually do in science class. Now, obviously, Aristotle and Galileo didn't really have the same ideas about motion. Galileo really improved upon a lot of these ideas. So, where Aristotle thought that forces kept things moving, Galileo had this other idea. He said that forces make things stop or change direction, and that it was this different thing called inertia that kept things moving. I'll give you an example. Say you're shopping in Superstore with a cart and you give it a big push. What's it going to do? It's going to keep rolling, but eventually it's going to slow down and stop. Now, if we're listening to Aristotle, he says that forces keep things moving. In other words, you have to keep pushing in order for it to move. So, question is, for Aristotle, once I let go of that cart, it should have stopped moving, but it kept going, right? It usually goes a few tiles before it slows down and stops, and this is where Galileo's explanation comes in. He believed that any object in motion had a property called inertia, which kept a moving object in motion without the need for continual application of force. Now, this explains why your cart keeps moving even though you've stopped pushing it. Let's go into inertia a little bit more. Now, this is the big concept that Galileo came up with, and inertia is the property of matter that causes it to resist a change in motion. So here's an example. Say I have a piano and it's sitting still. Well, especially a grand piano, that's going to be really hard to move. If I gave you a toaster, on the other hand, that's going to be actually pretty easy to move. Thus, the piano has a lot of inertia, and the toaster has less inertia, a little amount of inertia. And this all has to do with how easy it is to change its motion. It's really hard to get a piano moving, but it's really easy to get a toaster moving. Now, what is the main difference between a piano and a toaster? If you're saying the mass, you're correct. Inertia is very connected to mass. The bigger something is, the harder it's going to be to change the motion, and the more inertia it's going to have. Now, similarly, a semi-truck flying down the highway at 111 kilometers per hour is going to be really hard to slow down. Whereas if I have a mosquito traveling at that same speed, it's not going to be very hard to slow down. So even moving objects have inertia as well. So this means that a truck or a larger heavy object has lots of inertia, and a smaller object that's very light is going to have less inertia. So we can, by changing speed, that means I could be asking something to speed up or to slow down. Now, it's important to remember once again that an object's inertia solely depends on its mass. Galileo suggested that once a force acted on an object to start it moving, the object would keep moving until it hit something or until friction or some other resistance caused it to stop moving. Now, if you've ever, ran across a floor and socked feet and you eventually slow down, right? Maybe you keep moving for a little bit on that hardwood floor, but eventually you stop. And that is because of friction. Friction is an opposite force working against you to slow you down. So Galileo wasn't always content with just thinking and talking about his ideas. Like I said, he wanted evidence. So therefore, he would conduct experiments. One really well-known experiment that he did involved dropping a ball from different heights on a ramp. Now, Galileo used this inclined plane experiment to reason that once an object was in motion, it would tend to stay in motion unless something, like an outside force, stopped it. And this is how he kind of explained it. He would set up this ramp and drop a ball from a certain height. Now, what do you predict was going to happen? Take a minute and think. As soon as he dropped this ball, it would roll down the incline onto the straight area and then up the other ramp. It would actually go to the exact same height as what it was dropped at. Now, when Galileo changed the ramp size, he wanted to see what would happen to the height that the ball reached. Interestingly enough, it reached the exact same height. So, when Galileo dropped this entire ramp and just made it into a flat surface, he proposed that when he dropped the ball, he observed that it kept rolling. Now, his explanation for this is that the ball would continue to roll, especially if there was no friction, forever, or until something stopped it, like my hand, because it was not meeting the same height. So without any friction stopping this ball, or an outside force like my hand, this ball would continue to roll forever and ever and ever. Now, the next gentleman we're going to talk about is Sir Isaac Newton. And he's a little bit more modern, say from 1642 to 1721. He actually was born around the same time that Galileo died. And he had some pretty funky looking hair. Now, Galileo had some awesome ideas, but Sir Isaac Newton actually built off of these to create the 3 laws of motion that you are going to be hearing about for the next little bit. You may also remember Sir Isaac Newton as the gentleman who had an apple fall on his head and he went, "Eureka! Gravity!" The story is actually a little bit more complicated than that, but it makes for a fun story. So, once again, we also know that he formulated the law of universal gravitation, explaining that gravity was responsible for both the falling of objects here on Earth and for the revolution of planets around the sun. Now, Newton said that all moving objects move in a straight line path unless a force acts on them. So this means that when I push my cart away from me, it's going to move in the straight direction that I pushed it in. It's not going to, turn in any odd direction on its own accord. Now, a good example of this is if you were to be swinging a yo-yo in a circular motion, kind of like the image down here. If that string were ever to break, what direction is that yo-yo going to fly off into? Now, if my ball fell off the string right here, it's going to continue in a straight line path. The ball is not going to continue going around in a circle because that string is not keeping it there. So it would actually continue in a straight line from where the string broke. Similarly, if the string were to break down here, the ball would now continue in a straight line path into this corner instead. Another interesting fact is that Sir Isaac Newton actually created a new type of mathematics called calculus. So if any of you are taking calculus class next year or the year after, you can thank Sir Isaac Newton for that. But the one thing that we really always remember about Sir Isaac Newton is Newton's 3 laws of motion. And this is what we're really going to be focusing on for the rest of the week and a few days. Now, these 3 laws of motion are fairly fundamental to the way we understand motion today. In Newton's first law is known as the law of inertia, kind of giving a little tip of his hat to Galileo. Now, the first part of this law says that an object at rest will remain at rest unless an external unbalanced force acts upon it. These are things that you can keep saying over and over in your head until you memorize it, because it's very, very important. Now, the second part of this law says that an object in motion will remain in motion at a steady speed along a straight line path unless an external unbalanced force acts on it. Essentially, it's saying that if something is moving, it's going to continue in that direction until something hits it in the opposite direction or makes it stop by putting force on it. Like, say a car is sliding on ice. That car is going to continue sliding on that ice because there's no friction until it hits something to make it stop, like a light pole, or it hits a car going in the opposite direction. That would also make it stop. So in other words, objects are lazy. They like to keep doing whatever it is they are doing, unless an unbalanced force acts on it, right? So you could say the lazy student is going to sit on the couch and watch Netflix until the unbalanced force of some extreme homework forces them to get off the couch and start doing their homework. I don't know. That's just a silly example. Now, this law means that Aristotle was wrong. A force is not needed to keep an object moving. So it's important to note that all of these revisions help to correct Aristotle's initial idea and improve upon it. Now, friction is a force that is acting to resist that motion. So, say I was sliding once again in my fuzzy socks on my hardwood floor. If I didn't have any friction, I would actually continue to slide forever. So the only thing that's stopping me is that friction acting in the opposite direction to resist my motion and slow me down. An object you push will eventually stop because friction is acting to resist that forward motion. The object will slow down because of the friction and eventually come to a stop. So if you want something to slide forever, you have to get rid of that friction. So by adding something that's going to make it slippery, you can make something go further. For example, this is why you use water on a slip and slide. Otherwise, you wouldn't go very far. Now, forces cause a change in motion. They do not cause motion. That's important to also remember. So here's an example. Imagine your neighbor's car is stuck in the snow after a large snowfall. The tires are spinning, but the car is going nowhere. You find a friend to help you, but the two of you are pushing together does nothing to move the car. Just then, two more friends show up and help out as well. The combined push of all four people gets the car moving. If this happened, you would be applying Newton's laws of motion without even knowing it. So by having just you and your one friend, you may not be giving a big enough unbalanced force to get that car moving. However, when you have four friends pushing on it, you are now pushing hard enough to give an unbalanced force and to get that car moving again. In other words, you're getting over its inertia. So the inertia of an object is based on its mass. Remember, the more mass an object has, the more inertia that it has and the harder it's going to be to move. So say that car stuck in the snow has a large quantity of inertia. So it's going to take a large force to get it to move again, meaning you're going to need lots of people to help push it out. All right, now that we've talked about Newton's first law, we're going to move on to Newton's second law, also known as the law of acceleration. First part of this law talks about how the bigger the unbalanced force on an object, the greater the acceleration will be, right? Also known as if I push something really strong, it's going to go very far. If I push something just a little, it's not going to go very far. The second part of this law talks about how it's related to mass. In other words, the greater the mass of an object, the smaller its acceleration will be. So if I give something a big force, typically I'm going to get a big acceleration. I give a big swing, that golf ball is going to go flying. However, if I were to hit a fridge with that same golf club with the same amount of force, the fridge is not going to go nearly as far. And that's because my fridge has a bigger mass. It has more inertia, so its acceleration is going to be smaller. It's only going to move a fraction of the distance that my golf ball is going to. So, for example, let's look at that stuck car again in that snow. If that stuck car has passengers inside, they're going to have to get out in order to reduce the mass. By reducing the mass of the car, we are now going to be able to accelerate it more when you push. Now, we are going to talk a little bit about how to calculate force for Newton's second law in a day or two. However, we're going to quickly go over Newton's third law in this video, just so that we have a good summary of what all three laws are. So Newton's third law is the law of action versus reaction. Also known as for every action force, there is an equal and opposite reaction. To Newton, every force simultaneously receives a return force equal in size. So no matter what is happening, there's always an equal and opposite reaction. There's an equal and opposite force pushing back on you. Take these two objects, for example. If they're pushing on one another with a certain amount of force, the object on the other side is going to push back with the exact same amount of force. Think of it as objects acting like a spring. They naturally know to push back on one another with the exact same amount of force that is going to be pushed on them. So say I were to push on a wall with 100 newtons of force, that wall is actually pushing back on me with 100 newtons of force as well. As a result, we both stay in the exact same spot. If I were to push with more force than what the wall was, my hand would push into the wall. And if the wall were to push back on me with more force, then it would be pushing back against my hand. Now, and this happens in almost any object that you're pushing against. Say you were on some fancy rollerblades and you push against a wall or a truck, something with lots of inertia that's going to stay in the same place. When you push on something, it pushes back on you with that exact same force. And because you have less inertia, or you're lighter than the truck, you're the one that would be sent moving. So from this, I just want you to know that whenever you push on something, it's pushing back with the same amount of force because that is the reaction from your action. Another example of this is when you move forward. Now, in order to walk forward, you push your foot backward on the ground. Newton would call this the action. When you push backward on the ground, you're basically pushing back on planet Earth. And Earth now pushes back on your foot with an equal but opposite amount of force, also known as the reaction. Now, similarly to walking across the Earth, we can also take a closer look at something a little more fun, like skateboarding. So in this situation, what direction are we really pushing with our foot? And what are we really pushing on? We are pushing backwards and applying a force towards the Earth. And as a reaction, What's actually pushing us forward is the return. The Earth applies a force to us, pushing us forward as a reaction. Now, these examples remind us that only external forces can change an object's motion. This means that people can't actually push themselves forward. Rockets can't push themselves upward, or a car can't apply force to make itself stop. Instead, all of these cases include us pushing on something else, right? We don't push on ourselves to push forward, we push on the Earth. A rocket's thrust is usually pushing air against the ground, not a rocket pushing against themselves. And a car is not applying force to itself in order to make it stop. It's those brakes applying force to the ground. Now, once we apply this force, it pushes back on us in the direction we want to go, or in the direction we want to slow down. Newton's third law makes us go or stop, actually. It allows us to change our motion. So it can make us go forward and propel ourselves, or it can make us slow down. All right, everybody. Thank you so much for watching this video. I do have a few practice questions that you can look at in the next few days to help use Newton's laws to explain motion. We're also going to be watching a fun demo video in the next couple of days to help you see Newton's laws happen in real life. All right, everybody. I hope you're having a fantastic day and keep learning. Bye-bye.